All right, here we go, Friday. Okay, last chapter that we will cover this year. Um, so today we're going to do some interesting stuff. There's no homework to grade. We're going to do some really interesting stuff. Most of you have not been exposed to this ever before. We're going to have some new symbology, some new definitions. You may be familiar with some of the concepts, but the applications of that are what we're going to concentrate on today. All right, so here's the calendar. Basically, we got 2 weeks of classes, and that third week we'll review for the semester final, and then that last week we will take the semester finals. Starting, I guess, Monday, I'll show you the final schedule. Basically, how it's going to roll is that you're going to take one final every single day for that final week. All right, here's your homework. Please copy it down. Notice there's two parts here, written exercises and problems. Also, yes, you can use a calculator. All right, here we go. Now, most of you probably have never even heard this word before. It's called permutations, and some of you may have heard it. You don't really understand what it means. We're going to be talking about the mathematical definition of permutations today. All right, 3 objectives today. They shouldn't make much sense to you, but it certainly will make sense after the class. All right, now think about this. Okay, let's say you're at your house and you want to go to the movies, right? Movies are pretty darn expensive, and popcorn. It's outrageous spending $10 on popcorn. So maybe you want to stop at 7-Eleven and buy some popcorn first. So from your house to the 7-Eleven, there are 3 different routes that you can take. A really long one, kind of like the back way, kind of a medium one on a fast highway, and a shortcut that pretty much goes direct, but it's kind of slow. So let's say you had 3 different choices. Sometimes you go the long way, sometimes you go the short way. Once you get to 7-Eleven, to get from 7-Eleven to the movie theater, you got 2 different ways. Once again, a little bit longer, but it's on a faster road, and a short one, but you go through a bunch of subdivisions, that sort of thing. Okay, so the question to you is, if those are your choices and that's your plan, I'm going to go to the 7-Eleven first, buy some snacks and some drinks, and then go to the movies. How many different ways are there to get to the movie if this is what you have to do? Okay. Well, one way to figure this out is simply, it's called the brute force method in math. Simply, let's just trace out every possible way you can do it. So let's just say we take the medium way to get to 7-Eleven, and then once we're in 7-Eleven, we take, I don't know, the short way. Well, that's one way of getting to the movies, right? Well, another way would be, well, the same way to get to 7-Eleven, but in this case, take the longer road to get to the movies. Well, that would now give us a second unique way of getting. It's not the same way, it's different. But let's just say we didn't get to 7-Eleven taking that medium route. We took, I don't know, maybe we took the short way. Well, if we take the short way, then once again, we can go from the 7-Eleven to the movie using that direction. There's a third way, or the longer way. There's a fourth way. Or lastly, to get to 7-Eleven, we could take the longest route. Probably most of you wouldn't do that. And take the long route. There's 5, and then the other way, there's 6. It turns out for this particular trip, there are 6 different ways. There's 6 different ways to get to the movies. Okay? 6 different ways. Well, it turns out that if there are 3 ways to get to 7-Eleven, and there's 2 ways to get from 7-Eleven to the movies, that there were 6 ways. Take a guess at what's really going on there. Yes, you're correct. There's just some multiplication going on there. This process has a name in mathematics, literally. There's a whole branch of mathematics that deals with this type of math. This technique, right, of counting the number of ways to get from one place to another, and it can be further shown for. It's not just for trips. It can be used for other things that you'll see in this class. This is called the counting principle. Write this down, please. The counting principle says this, and notice it's not principle as in the school principle. The counting principle, that if there are m ways of doing one way, that means if there's so many ways of doing your first task, and n ways to do another, and there's n ways to do the second task, it turns out there's m times n ways to do both things. And we just found that out with our little trip to the movie theater. There were 3 ways to get to 7-Eleven, 2 ways to get to the movie. Therefore, there were 6 ways of getting from your house to the movie theater. Okay, this is called the counting principle. We will be using this the entire day today, and it's not very hard to understand or even see how it works. So here's an example. Uh, you'll see this a lot in 7th and 8th grade, and even in 9th grade test. They'll give you some clothes, and they'll say you have X number of shirts, you have Y number of pants, and then they'll ask the question, how many outfits can you make? Okay. Obviously, they're not taking into account things that match or things that don't match. They're just saying literally how many different ways can you get dressed, right? Well, we're simply going to use the counting principle. The counting principle says that if you have M ways of doing task 1, the shirt, and N ways of doing task 2, the pants, how many different outfits can you make? Well, there's 3 shirts, there's 4 pants, therefore there's 12 different outfits. Make sense? That is an example of the counting principle. Here's another one. They love these, right? They love this, travel and maps. If there's so many ways of getting to point 1 and so many ways of getting to point 2. So even though this is a word problem, the visual of this is pretty much the same as the one that I did for the house to the movie theater. So it says Ben can take any one of 3 routes. There's the blue. I'm not good with colors. There's 3 ways of getting from S to T, and there's 1, 2, 3, 4, 5 ways of getting from T to H. It says if he doesn't retrace his steps, meaning like you can't go the same way, right? How many different ways are there to get this? How many possible ways are there for Ben to walk home from school? So S is school, H is home, right? So this is still just the counting principle. So how many ways are there getting from S to T? Well, there's 3 ways. How many ways of getting from what does the T stand for? It stands for the town center. How many different ways are there getting from the town center to H's home? There's 5 ways. So this is 3 times 5, which is 15. So there's 15 different unique routes of getting from his school to his home if he stops at the town center. Oh, the fun doesn't stop there, right? This is another common one. It'll give you a certain item, and usually it's a car, and they'll say that there are different versions of the car. For instance, there's a sedan and hatchback. It comes in a whole bunch of different colors, and then there's different model numbers. Well, once again, this is just the counting principle, but you're probably saying, well, wait a minute. There's 3 different things here. So the counting principle can be continued. It's not just always 2 different tasks. Sometimes there's 3, 4, 5 tasks. So in this case, if we were to pick a car, there's 3 tasks you have to pick. You got to pick whether you want a sedan or hatchback. You got to pick the color, and then you got to pick the model, whether it's a GL, SS, or an SL. Okay? It's still the counting principle, so we just put another letter there, M times N times O, but it's the same principle. M will be the type of body style. So how many body styles are there? There's 2, sedan or hatchback. How many colors are there? There's 5. How many models are there? There's 3, and then you simply do the math. So 2 times 5 times 3. 2 times 5 is 10, times 3 is 30. There's 30 different cars here, right? And you're like, well, wait a minute. Only thing is changing is color. So, okay, depending upon your definition of a unique car, but most people would consider that a red car and blue car are 2 different looking cars. However, I shouldn't say however, but the most popular one that you will see is, I don't know why math people do this, but apparently we like pizza a lot. You will see this question so often. And the scenario involves always a pizza. You got a pizza, and there's different sizes, or there's different types of crust, or there's different types of toppings. And the question is, how many different pizzas can you order? In fact, if you go on to Domino's or to Pizza Hut, they always tout that they have so many different number of thousands of pizzas that they can make. And they're basically just using the counting principle. So let's see what's our scenario here. So she wants to get a pizza. She can order either a large or a medium. There's the size. So it's a choice of 7 different toppings and 3 different types of crust. So how many different pizzas could she order, right? Well, it's the counting principle. You have 3 choices to make. You have to make the size. So there's 2 different sizes. You have the different types of crust. There's 7 different types of crust. There's 7 different types of toppings, and there's 3 different types of crust. So once again, it's 2 times 7 times, it's the counting principle. 2 times 7 is 14. And 14 times 3 is 42. So this particular place can make 42 different pizzas. Tonight for homework, there's a few like this. It's pretty simple. It's just the counting principle. Okay? And if that's all there was, then life would be good because this is pretty simple. So I want you to take a deep breath. We're about to move on to something, new notation. You've never seen this before. Some of you have probably noticed this button on your calculator. You just don't know what it's for. Okay, so I need you to write this down. It's called permutations. So a permutation is an arrangement of things. That means you literally have some things that you will arrange, and their arrangement must be in a specific order. That means there's a first item, there's a second item, a third item, so forth and so on. And their order matters. The order matters. The second definition is called a combination. A combination it's still an arrangement, but there is no order. That means there's not a first thing or a second thing. There are just things. The order does not matter. These two words, permutations and combinations, most students will quickly learn how to do these calculations, but they will have a hard time telling the difference between a combination and a permutation. So the easiest way is, well, make sure you have a resource card. All right. I don't have any good, and hopefully one of you guys can. I've asked my students every year, somebody come up with a good way of remember permutations and combinations. All right. So here's my example of a combination of permutation. So let's say you have three items. I've got a square, a circle, and a triangle. Combination means this. Order doesn't matter. I'm going to ask you to choose some of these items, but their order doesn't make a difference. So for combination, if I were to ask you to choose two of those items, you might choose the square and the circle. For combination, choosing a square and circle is the same as choosing a circle and a square. It's the same two items. Just imagine a bag, and you're going to pick two items and put them in a bag. It doesn't matter whether you choose the square first or the circle first. You still have a square and a circle in the bag. Combinations has no order. Is that the only two things I can pick? Well, no, I could also pick a square and a triangle. That's certainly different than a square and a circle. I've got two different items now, right? And then lastly, I could pick the circle and the triangle, right? So it turns out that if I ask you to choose two items out of three, that there are three different combinations there. And remember, order doesn't make a difference. Choosing a circle and a triangle is the same as choosing a triangle and a circle. However, when we switch to permutation, this is where the order matters. So, for instance, if I were to choose a square and a circle, that is not the same as choosing a circle and a square because the order matters. The first thing you choose is a square. Well, that's not the same as a circle. So, permutation I think of it as when you line things up. If you were to line things up from left to right, the order would make a difference. Permutation, the specific order matters. Combination, the order doesn't matter. Is that the only two permutations? Well, no. We could also pick a square and a triangle, or a triangle and a square. We could also pick a circle and a triangle, or a triangle and a circle. There are 6 different permutations here. Now, it would be easy for you to say, oh, there's always double the number of permutations, combinations. Not true. Okay? This particular case, that's true, but it's not always true. There are way more permutations than there are combinations. Okay, another example of permutations where order matters is another example I like to use is the movie one. Let's say your mom says, all right, let's go to the movies. You can bring 2 friends. So it doesn't matter whether you pick, friend 1, friend 2, or friend 2, friend 1. It's still the same 2 people going to the movies with you, right? That's an example of a combination. An example of a permutation is when you get to the movies, which seat you choose. If you pick the middle seat, or you pick the left seat or the right seat, that's different, right? Those are 3 different options right there. So you have lots of different permutations. You only have a few different types of combinations. Here's another example. Let's say you have 3 things, 3 different colored cards. We'll call these cards. And I ask you to pick the 3 cards, like literally pick them up, all right? Well, how many permutations is that? Well, think about it like this. The first thing you have to do is pick your first card, right? Your first choice. And you have 3 to choose from, right? And then you put it down somewhere. So let's just say that X there represents my first choice. Well, when you come to your second choice, choice number 2, do you have the same number of choices? And the answer is no, because there's already 1 card put down. So now you only have 2 choices to make. right? Your second card you put down right there. When you get to your third choice, well, there's only one card left, and it goes right there. Notice I don't know what colors go where because I don't know what my choices will be. But I do know this, right? When I make my first choice, there's 3 cards to choose from. When I make my second choice, there's 2 cards to choose from. When I make my last choice, there's only 1 card left. Once again, this is the counting principle, okay? It's 3 things to choose from, right? So you got choice 1, choice 2, choice 3. So when you make your first choice, how many cards are there to choose from? There's 3 cards. When you make your second choice, there's only 2, and your last choice, there's 1. Well, counting principle says that's 3 times 2 times 1. There are 6 different ways that you can choose 3 cards if you're given 3 cards. Make sense? What would happen if we had 4 cards? Okay. Well, if you had 4 cards, you got 4. Notice those 2 patterns. Kind of interesting. When there were 3 cards, the counting principle said there is 3 times 2 times 1. When there's 4 cards, the counting principle said there's 4 times 3 times 2 times 1. Do you notice the pattern there? In math, we actually have a word for this, and we actually have a key on the calculator that does this for us. Okay? Write this down, please. This is called a factorial. A factorial is a shortened method to write the multiplication of descending order consecutive numbers to 1. Right? A shortened method to write the multiplication of descending order consecutive numbers to 1. Now, some of you that probably made a whole lot of sense. Others of you had to hit the pause button and read that, and it still doesn't make sense. All right, let me confuse you some more. We have a symbol for factorial. The symbol for factorial is an exclamation mark. The exclamation mark is called the factorial symbol. You're like, well, wait a minute, there's an N there. The N represents your starting number. So that is read 4 factorial. What does it mean? Well, the definition says 4 is the number you start with, 1 is the number that you end with, and we write consecutive numbers, and then everything is multiplied. Yeah, that's what factorial means. The number, the N, is your starting number. It's descending. It descends all the way down to 1, and then you put multiplication symbols. Okay? We don't skip any numbers. So let's see. 4 factorial, 4 times 3 is 12, times 2 is 24. Notice I don't have to multiply by 1. 3 factorial, well, that's 3 times 2 times 1. There's a shortened way of writing what we just wrote for the counting principle. Mathematicians are all about doing things easier. It's certainly easier to write 4 exclamation point than write 4 times 3 times 2 times 1. Right? There you go. That's what a factorial is. So here's an example. Tonight for homework, you're going to see something like this. They're going to say, well, what's the answer? Well, here's how you handle that. 5 is your starting point. 1 is always your ending point. So we go 5, 4, 3, 2, 1, and put multiplication symbols. You're like, well, do I ever need to write the 1? Well, I mean, technically, by definition, the answer is yes. But remember, anything times 1 is itself. So let's see. 5 times 4 is 20, times 3 is 60, times 2 is 100. Wow, we got big really quickly. Factorials get large very quickly. There is a factorial button on your calculator. I'll let you explore it all by yourself. I'm sure Haven's already got this figured out. You can't do a large factorial. You can't do 9,000 factorial on your calculator. Blue smoke will come from it. Try it. See what happens. It just ends up being a really large number. Okay, you, tonight for homework, will have to do smaller examples. So, go ahead, do 7 factorial all by yourself, and then answer the next question on the Google Forms. Did you get it? All right, for those of you that were struggling, just remember, you start with 7, you go down to 1, decreasing by 1 each time, and you put multiplication symbols. Turns out that 6 factorial, the difference between 6 factorial and 7 factorial is huge, right? This is 5,040. It's really large, really quickly. But that's how you do factorials. Any questions? Send me an email. Let me help you. Okay. So what? Great. We know how to do factorials. How does it make our life a little bit easier? All right. I'm going to give you one example. Well, actually, a couple different examples. So we've been doing these things called permutations. That's selecting things where order matters. So here's an example of a permutation. It says, how many different ways could you choose 4 cards if you had a deck of 10 cards. So it says you want to choose 4 cards and you're starting with 10. So once again, there's there's a very long sentence that illustrates or represents a mathematical problem. Okay, how many different ways can you choose 4 if you start with 10 things? Mathematicians, once again, have invented a shorter way of writing that one problem. Like, I don't want to write all those words. I just want to have something that represents this problem. This is what we use. Once again, this is a button on your calculator. All right. This means, well, the capital P stands for permutations. Now, they didn't do a good choice of the N and the R. However, the N stands for how many are you choosing from, and the R stands for how many are you going to choose. Trust me when I say don't panic yet. It's not that bad. P will always be the capital letter P, but N and R, there will be numbers there. So let's see in our problem. P will be the capital letter P. It says how many you're choosing from. Well, we're choosing from 10 cards, and we're supposed to choose 4 of them. So 10P4 is how you represent this problem. Tonight for homework, they're going to give you 10P4 and ask you, well, what's the answer? Okay? We better write this down. All right, so let's write this down. This is called the permutations formula. The permutation formula is called the NPR formula, right? And capital P stands for permutations, and it will always be the capital letter P. That doesn't change. What will change is the N and the R. The N is, well, how many are you choosing from, right? How many things do you have to choose from? And the R is, well, how many do they want you to choose? If you have this right here, what is written on this slide right next to you, you'll be able to do the homework fine. But it will take you a few of these to commit this to memory, okay? So go ahead and pause the video, listen to it again if you need to, but make sure you have this written down and next to you before we try the other problems. All right, well, let's do this problem. So you'll see, this was the problem 10P4. So 10 choose 4 permutations. Once again, we're going to use the counting principle. It told us, I can tell from the problem, I need to choose 4 things. In order to choose 4 things, the first thing you have to do is make your first choice, right? Well, how many cards are there to choose from before you choose the first card? There's 10 cards there. When you make your second choice, how many cards are there to choose from? Well, there's not 10 because you already chose one. So there's 9 things to choose from. Your third choice, now there's 8 things. You see the pattern? And your fourth choice, there's 7. How come I didn't do a fifth and a sixth? Because it only told us to choose 4 cards. First, second, third, and fourth choice. But the first one, there's 10 cards, right? The second time, I've already chosen one of the cards. There's only 9 to choose from. This is the counting principle once again. So how do you do this, right? Well, you simply take those numbers and you multiply them. 10 times 9. This is not a factorial, right? It kind of looks like it, but we didn't go all the way down to 1. Eventually, it could be a factorial if it was 10 choose 10. 10 choose 10 would be 10 factorial. But in this case, it's 10 choose 4, so there's only 4 choices. 10, 9, 8, 7. Okay? We do that math. It's a big number. I mean, think about that. There's 10 cards. There's 5,040 different ways of choosing 4 cards. That's crazy. Here's another example. We like this example. There will be something like a bag, and there will be letters inside of a bag. And usually there will be a word that those letters spell. So, for instance, football. So there are the letters Football in a bag. And it says reach inside and choose 3 letters. How many different permutations are there? Well, remember, we can write this as 8P3. 8 is the number, 1, 2, 3, 4, 5, 6, 7, 8 letters. And I want you to choose 3 of them. So this always happens the same way. You got to make your first choice. Well, how many letters are there to choose from in the bag when you start the game? Well, there's 8. There's 8 letters in there. Football. When you make your second choice, remember we're going to choose 3. When you make your second choice, now there's 7. You make your third choice, now there's 6. So using the counting principle, that's 8 times 7 times 6. Okay? That's how it's done. You want to try this one by yourself? All right. Just remember tonight for homework, they're going to give you some that are in this form. This is the problem. You got 9 friends, and you got to have 3 people sitting next to each other in the movies. How many ways can this be done? If you have 9 friends and they're sitting next to each other, right? That would be 9, choose 3. So how many different permutations is that? Well, how many are there to choose from? You make your first choice. Someone has to sit down first. So when the first person sits down, there's 9 different people. I'm sorry, there's 9 different choices to make, right? Because you got 9 friends, right? When the second person sits down, well, there's 8 friends you can choose from. And when the last person sits down, there are 7 people to choose from. That's 9 times 8 times 7. This is 9, choose 3. Does that make sense? Well, the only thing left to do is that math. 9 times 8 times 7 is 504. Think about that, right? I don't know if you have 9 friends, but if you have 9 friends, there's 504 different ways that 3 of them can sit down. That's a lot of choices. All right, look at this one. You got 5 books on a bookshelf. How many ways can they be arranged? This is crazy. There's 5 books. How many different ways can you arrange 5 books? Well, remember, arranging books means to line them up. That means order matters. That's 5, and we're using all the books this time, so that's 5, choose 5. Well, using the counting principle, that is 5 factorial. That's 5 times 4 times 3 times 2 times 1. The first book you put up there, there's 5 books to choose from. The second book, now there's 4. The third choice, now there's 3. The fourth choice, now there's 2 books left. And the fifth choice, there's 1 book left. 5 times 4 times 3 times 2 times 1, which is 5 factorial, by the way, is 120. There's 5 books, but there's 120 different ways to arrange them. Okay, so here's what you got in front of you. This is the next question on the Google Forms. Please answer this, right? Remember, the first one is how many things you have, and the second one is how many you are choosing. Use the counting principle to simplify each permutation. Go ahead. How'd you do? For me, I always look at the number on the right first. I don't look at the number on the left. I look at the number on the right. It says I need to, the top one there, I need to pick 2 things. And I have 6 things to choose from. So 6 and 5, right? I'm just going to start with the 6 and count down. I got 2 things I got to choose. So notice there's 2 numbers here. 6 times 5 is 30. There's your answer. The second one, 6 is my starting point. I got to pick 6 things. There got to be 6 numbers. 6, 5, 4, 3, 2, 1. Hey, that's 6 factorial. That's 720. Think about that. 6 books. How many different ways can you arrange 6 books? 720 different ways. That just, when I first learned this, it just really was eye-opening, the number of different permutations there are. Okay. Okay, last one. Well, let's see. We got to choose 3 things, but there's 52 to choose from. So that first choice, there's 52. The second choice, 51. And the third choice, there's 50. I'm just counting down by 1, and I'm picking 3 of them. 52, 51, 50. Well, that's going to be a big number. Holy moly. 132,600 different ways. But that's because you have 52. I chose 52 because that's how many cards there are. So if someone offers you a deck of cards and says, pick 3 cards, that's how many different ways you can pick 3 cards. 132,600 different ways. Can you wrap your head around that? That's crazy. Right. Another example would be license plates, right? License plates follow a format. I don't know what the format is in Colorado, but there's numbers and there's letters. There's only 9 numbers to choose from, right? And there's 26 letters, right? So you would think there's not that many combinations and permutations. There's lots of combinations and permutations. All right. Oh, by the way, that's it for the class. Pretty easy, right? All right, so here's your homework. Remember, it's 2 parts, both the written and the problems. So make sure you do both of those. If you have any problems, send me an email. And if not, I'll see you guys on Monday.